Namaste everyone, welcome to Wave Optics class. We have seen different properties of light by taking it as a wave, right? Wave nature of light. So because of that reason that we can take light as a wave, we were able to explain different phenomena of light like diffraction and interference. By using Huygens secondary wave principle, we were successfully able to explain how diffraction occurs and how interference occurs. Now today it's our class. In our class we are going to discuss about the new property of light called polarization. This is another property of light which can be explained using wave theory. Namaste, right? You can see me now, right? And Young's double slit experiment, interference and diffraction, all these things, they are the real experimental observations which made wave theory to become very strong. Because using only wave theory we were able to explain diffraction and interference. Now there is one more called polarization, which said that light is a transverse wave. Polarization is one of the property of any wave, and it's not only observed in light, it is observed in many waves. Polarization is a property which is observed by only transverse waves, not longitudinal waves. And you will come to know why longitudinal waves cannot show polarization. You will come to know about it, because once you understand polarization, you will understand that polarization cannot be seen in longitudinal waves at all. It's not possible. What do you mean by polarization, first of all? So now in polarization, if you want to see, you should know what light is made up of, right? Light is made up of timely varying electric and magnetic fields. So if you combine magnetic field and electric field together, and of course they are very close friends, magnetic field and electric fields are very close friends. If you pass current through a conductor wire, it produces magnetic field around it, you know it. And so whenever there is electric field, it produces magnetic field. Take a coil, connect it to a galvanometer, vary the magnetic field around the coil, electromagnetic induction, you might have studied it in SSLC, and that change in the magnetic field induces current in the coil. So magnetic field calls its friend, right, in electric current. And electric current always carries its friend, that is magnetic field. So they are very close friends, and they are always perpendicular to each other. The direction of electric field, direction of magnetic field are perpendicular to each other. Now if this electric field and magnetic field are continuously changing with time, continuously varying with time, then that leads to light. That is electromagnetic wave theory given by Maxwell. James Clerk Maxwell gave a new theory called light is a wave, he said, but it is an electromagnetic wave. So if a light is propagating in this direction, so this is the speed of light, c, then the electric field, if it is like this, then magnetic field should be like this, and all are mutually perpendicular to each other. So light is made up of, suppose the light, a forefinger represents the direction of light, then the electric field, if it is like this, magnetic field is like this. And when that light comes and falls on your retina, it is that electric field which creates some potentials and makes the visibility. So whenever you see light coming from an object, you feel the sensation of vision, right? When you can see the object, and the retina can detect it, it can send the signals and the brain can recognize what you are seeing. That is possible because of this electric field. And what about the electric field and magnetic fields when combined together to form light? Are they remaining the same everywhere? No. As soon as the light is passing from one point to another, this electric and magnetic field at a particular point is not in constant value. It is continuously changing with time. Just observe water ripples on the surface of a tank. If you just take a stick and put it into water and move it 3 or 4 times, then you will find water ripples, right? What about water molecules? Are they keeping at the same point and producing water ripple? No, they will be keeping on vibrating one by one, and they will not be steadily standing at a particular place. It goes to the top, comes down, and constantly vibrating. That makes the ripple fresh always. Similarly, if light has to move forward, this electric field and magnetic fields, they keep on changing. So if you find the electric field at a particular point little later, electric field will be 0, and after some time it will be negative. After just a fraction of a second, it will be something else. So the continuous variation of timely varying electric and magnetic fields produce light. That is electromagnetic wave, and we are interested with electric field here because that creates the sensation of vision. And when electric field reduces to zero, surprisingly magnetic field also reduces to zero because already they are very good friends. When magnetic field grows to a maximum value, electric field also grows to a maximum value, so they are in phase. Now at this point of light, electric field is highest, magnetic field is highest. What about little earlier? Here at this point, electric field is little bit weaker, magnetic field is also weaker. Here much more weaker, here still weaker, here zero. What about behind it? Here at this point the electric field is negative and magnetic field is negative. Electric field is more negative, magnetic field is more negative, much more negative, much more negative, like this. So if the magnetic field grows and becomes like this, electric field grows and becomes like this. So at this point, electric field and magnetic field will be fluctuating every time, and at this position, at different points of light, the electric field and magnetic fields are like this. Very next moment it will not be so. If very next moment, if you take the photograph of electric field and magnetic field, which is not possible, you can't take the photograph. Simply imagine, if you can take the photograph of electric and magnetic fields, very next moment, electric field and magnetic fields will be entirely different. It might have gone to zero here, it might have gone maximum here. So the peak may be here now at that moment. As if the crest in a water ripple may not be permanently at a place. It may be somewhere else, and at one moment it is here, next moment it is trough. So timely varying electric and magnetic fields produce light. How many times they vary per second? That is the frequency of light. So what do you mean by frequency? Frequency is always number of oscillations made in a second. What is frequency of light? What is there vibrating in light? This is what is vibrating in light. It is a vibration of electric field and magnetic field per second. They keep on doing that, and it is very high frequency, and they do it so they go to maximum, minimum, zero, and electric field becomes highest, zero, minus highest, zero, and that keeps on changing, and that how many changes per second, that is called frequency of light. So so light is a combination of electric and magnetic fields, and electric, magnetic field and the direction of propagation of light all are mutually perpendicular to each other. Now the question is, if the light is so, when it falls to your retina, electric fields are producing some amount of potentials and sensation in the eye, and they will be producing signals, and that will be carried to the brain, and that creates the sensation of vision. Now in light, suppose the electric field is like this and magnetic field is like this. Sir, what is this electric field and magnetic field? Of course, in the diagram we have shown it symbolically by arrow marks. Whether you get electric field and magnetic field only in these directions, don't you get electric field and magnetic field in this direction, electric field here and magnetic field here? Don't you get that in these directions, a new type of electric and magnetic field? Don't you get electric field and magnetic field in these directions, this electric field corresponding magnetic field perpendicular? Don't you get electric and magnetic field in this direction and in this direction, sir? Possible. Electric and magnetic fields will be found in all directions. It need not be only in one direction. Suppose a beam of laser is entering into the board like this. Imagine, this is a plane and it is coming like this. If the light is coming and hitting on the board, producing a dot-like arrangement here. Now if you try to find out the electric field here, there is a corresponding magnetic field here. If you try to find out an electric field here, definitely there is a magnetic field here. And if you try to get an electric field here, definitely there is a magnetic field here. I can have many colored chalks. One is remaining, yes. Electric field here, there is a magnetic field here. What do you mean by that? Electric fields and magnetic fields are perpendicular to each other. They are aligned in all directions. If light is coming towards you like this, and this is the path of light, if there is an electric field here, magnetic field, electric field, magnetic field, electric field, magnetic field, electric field, magnetic field, every direction. If electric and magnetic fields are aligned in random directions, then it is called unpolarized light. A light which contains vibrations in all directions. And from here onwards, if I say vibrations. It is electric field vibrations. Why vibration? Because electric field is continuously changing with time. Once it becomes stronger, another time it becomes zero. So it keeps on changing its value. So the thing is, when a light travels in a particular direction, if the electric and magnetic fields perpendicular to its direction of propagation are found in all planes, for example, when the light travels like this, I can find out electric field in this direction, in this direction, in this direction, in this direction. Everywhere I can find out the electric field and magnetic field. Such a light is called unpolarized light. Now, what do you mean by polarization? Restrict all these electric field vectors into a particular plane. What do you mean by plane here? Very simple. Say this purple color is the light which is traveling towards you, and this is electric field, right? In which plane this electric field is now? Electric field is in this plane, correct? And if I search an electric field like this, is there any electric field like this? Yes, there is electric field in this plane. If I search an electric field like this, is there any electric field like this, sir? Yes, light is coming like this towards you. Is there any electric field here? Yes, sir. So electric field is found in all the planes. It is found in this plane. It is found in this plane. It is found in this plane, every plane. Restrict it to a single plane. What do you mean by that? If the light is coming towards you, towards you, restrict the vibrations only here. Sir, do you find any electric field in this direction? No, sir. Like this? No, sir. Only like this. How is it done? It's very interesting. Now, we will take a wave generated by ourselves. Take a wire, tie it here. Simply a thread is enough. Tie the thread at a particular point. Go on vibrating it. When you vibrate it like this, what type of waves are produced? Whether these type of waves are produced, correct? Okay. At the point where we tie it, no vibrations. Okay. Now wave it like this. What type of waves are produced? So it is when it is vibrated like this, these waves are produced, right? They move. Vibrate it like this, little bit cross like this. So vibrate it like this. Okay. Now when you vibrate it like this, these waves are produced, right? All types of waves are produced now. So I'm just oscillating this wire or thread like this, like this, like this, like this, everywhere, zigzag. And once the thread waves like this, once the thread waves like this, another time like this, another time like this, it's an unpolarized wave. And now if you go on in the thread, if you go on searching the wave, is there any wave like this? Yes, there is a wave like this, because sometimes I'm vibrating it like this also. Is there any wave like this? Yes, there is a wave like this. Is there any wave like this? Yes, I am vibrating like this anywhere. It's an unpolarized wave. The vibrations are in this plane, vibrations are in this plane, vibrations are in this plane, everywhere. Vibrations are not confined to a single plane. Vibrations are found in all the planes. And that is an unpolarized wave. The simple wave what I have produced. Okay, now how to confine it to a single plane? Very simple. You pass this thread through a cardboard which is having a slit like this. The slit is so thin that only thread can pass through that. You take a cardboard, make a small slit here, small gap, so that only thread can pass through it. So if you make such a hole, what happens is, now you vibrate it here. Vibrate it like this, like this, like this, in all directions. Till here, vibrations can pass through. Right? Up to here, the vibrations can pass. What about from here? From here onwards, this hole, which is only as thick as the thread, will block all these vibrations, these vibrations, these vibrations. Now the thread has the freedom to vibrate only like this. Only these vibrations are allowed to pass through, and here onwards you will have fresh only these vibrations in this plane. These vibrations are cut, these vibrations are cut, these vibrations are cut. Correct? This is polarized. This is unpolarized. Am I right? So the wave in which vibrations are found in all the planes is called unpolarized wave, and the wave in which vibrations are found in only one plane, restricted to a single plane, is called polarized. Polarized wave, not light I am talking about. Now, how to confine all these electric field vibrations? And just now I have told, sir, if you put a light like this, is there any electric field like this? Yes, there is an electric field like this, there is an electric field like this. So in a light which is moving in perpendicular directions, in all directions, in any way if you observe, there are electric field vibrations. It is an unpolarized wave. Now, how to restrict all these electric field vibrations to a single plane? That is a challenge now. You have some materials in the nature in which all the molecules are arranged in a particular order. So you don't have all the materials of this characteristic. There are some materials in which the axes of all the molecules are in the same direction, like this. If the molecules are arranged like this, axes of all the molecules are parallel to each other. Now if you pass a light, a beam of light through such a material, what happens is that material, suppose this is a line along which their axes of all the molecules are arranged. The light, the vibrations of electric field vibrations of the light, which are parallel to the molecules, are absorbed, and the electric field vibrations of the light, which are perpendicular to the axis, are allowed to pass through. So if you put a light which contains electric field in this direction, electric field in this direction, electric field in this direction, electric field like this, like this, like this, like this. This is unpolarized light. Hope you can follow this, right? If you put a light into this type of crystal or material, transparent medium, unpolarized light, which contains vibrations, electric field vibrations in all directions, what happens is, the vibrations which are parallel to this axis are absorbed. Vibrations which are perpendicular to the axis are allowed to pass through. So light which comes out of this will contain vibrations only in these directions. This is polarized and this is unpolarized. And I call this axis as the pass axis of the crystal. Pass axis of a crystal is always perpendicular to its axis of the molecules, right? Because only the electric field vibrations, electric fields which are parallel to the axis of the molecules are absorbed, not allowed to pass through. Perpendicular to the molecular axis, those vibrations are allowed to pass through. So pass axis of the crystal is the axis, okay, I can put it like this rather. Pass axis of the crystal is that axis along which the vibrations pass through, and this axis doesn't allow. So this is a characteristic of the material, and it does so you can get a polarized light. So a polarized light contains electric field lines aligned only in a particular plane. If the electric field lines are restricted to a particular plane, see, this is the plane where you get electric field lines, right? You don't get any electric field lines in this plane. Do you get any electric field lines in this plane? There is no. Do you get any electric field like this? So if I continue like this, this is the electric field. No electric field like this. This is cut off. Only this is sent out, right? So restricting the electric field vibrations to a particular plane is called polarization, right? And the beam of light which contains electric field vibrations in a particular plane is called polarized light, and the beam of light which contains these electric field vibrations in all the planes, like this, like this, like this, that is called unpolarized light. Now, how do we represent this polarized and unpolarized light in our day-to-day life? How do we do that in our papers or notes? How do we represent it? Because whatever we see in the nature and whatever we write it in the paper are different. So how to represent the electric field? See, this is unpolarized light. A ray of light incident normal to the board and going into the board. Okay, this is okay. Shall I write it from here? You can see it here, right? So this is a light which is incident on the board, a dot, and electric field vectors like this. Arrow mark represents vectors, electric field, because they have direction. This is unpolarized. Okay, and another ray of light incident like this, containing electric field lines like this. This is polarized, but this may contain electric field lines like this way also. So put a dot here. What does dot mean? Dot means that there are field lines like this way also, which cannot be drawn in the paper. Unpolarized. And this is the direction of light, right? So this arrow mark is also must. These arrow marks also must. Okay. Then how do you represent unpolarized light, sir? Only unpolarized light. Where is the vibration plane? This one. Where is the polarization plane? What do you mean by polarized? Plane of polarization. The plane in which there are no vibrations is called plane of polarization. What is the plane of vibration? Plane of vibration is the plane in which there are vibrations. Okay, sir, this one. Is it unpolarized? No, it is polarized, because contains vibration only in one plane. This is how do we represent. So unpolarized, light going perpendicular to the plane of the sheet, light going on the plane of sheet, unpolarized, unpolarized, polarized. Sorry, polarized, polarized. Okay, if you put dot here, gone, right? Now, so polarization definition, restricting the electric field vibrations to a particular plane. And what is a polarized light? Light which contains electric field vibrations only in a single plane. Polarization is a property in which vibrations are restricted to a single plane. Now, another thing. If a wave shows a property of polarization, it should be a transverse wave. Initially, Huygens said that light is a longitudinal wave, but later on somebody said that light shows polarization. How could it be a longitudinal wave? And Huygens corrected it. It should be a transverse wave, because only transverse waves can show polarization. So the property, if you get a question like this, the property which shows that light is transverse. Tell me the property of light which shows that it is transverse. It is polarization. Light shows polarization. That's why it should be a transverse wave. Why, sir? Why can't longitudinal waves show polarization? Very simple. See, what do you mean by a longitudinal wave? Longitudinal wave is a wave in which vibrations are parallel to the direction of propagation of the wave, correct? So if you have a loudspeaker here, the membrane of the loudspeaker vibrates like this, and the nearby air molecules start vibrating, and like this. So the direction of propagation of the wave and the direction of propagation of the wave and the vibration are parallel to each other. So that's why it is called longitudinal wave. Whereas the ripples on the surface of water molecules vibrate like this, and the disturbance is carried like this. Vibration is like this. They are perpendicular, 90 degree. So this is called transverse wave, right? So if you have a thread like this, and if you start vibrating it like this, or like this, and like this, keep on vibrating it, produce random waves like this and all. And if you pass it through a cardboard having a very small slit like this, only these vibrations will be carried out, right? Now suppose you produce a longitudinal waves using a spring. Suppose the spring is like this. Best example for longitudinal wave is a spring. And if you just push the spring and pull the spring like this, push it and pull it along the direction like this, then what happens is, at some places the spring windings will come closer, and some places they move away, so like this, right? So this is called compression, this is called rarefaction. Now pass it through a cardboard through which this the spring thickness can pass, right? Pass it through a cardboard. Okay, I will make it clear. Okay, like this. Pass it through a cardboard. In whatever the way you hold the cardboard, either like this, like this, like this, like this, vibrations will pass. Just think of what is to be polarized here. Already it is polarized, right? Already the direction of propagation is in a single direction, and it's in a it's moving in a particular direction, and there is nothing like polarizing here. Already it is in a particular direction. So now if you hold this cardboard like this way, or like this way, like this way, anyway, once this spring can pass through this hole, vibrations will pass. Simply you should keep on vibrating it, that's all. And nothing can stop it by using a slit like this. Whereas here, you can stop these vibrations now. And if you turn it, those vibrations will pass. When you turn it like this, right, these vibrations will be cut off. You can cut some vibrations. Transverse waves can be polarized, not longitudinal waves. So if a light shows a property, if any wave shows a property of polarization, it should be a transverse wave. So the property of light which makes us to enable to show that it is transverse is polarization. And now suppose you have a polarized light. Suppose if this if you get some crystals like this, see, you can get, sir, through which type of material I can pass a light so that it gets polarized. The thing with polarization is, sir, so many electric field lines are absorbed when it is passed through a sheet. What about the outcoming light? Will it be stronger? No, definitely its intensity will be less. So intensity of the light coming out of the sheet, that polarizing sheet, and we call it as polarizer, right? The intensity of the light coming out of the polarizer will be definitely much lesser, because the many of the electric field lines are lost. It has been absorbed by the material. Now, does it mean that intensity of some light is less? Is it polarized? No, we can't say. Intensity will decrease because of many reasons. Now, whatever the light that we receive in our nature, we receive light from the windows, we receive light reflected from a mirror, we receive light from a bulb, from the sun, and all, scattered light from the atmosphere. Whether it is, whether those light are polarized or not, how to test, sir? How to see? Because for bare eyes it doesn't appear polarized, because we can't see these electric field vibrations at all. Then how to test whether a light is polarized or not? Now let this be a sheet, and we get so many sheets. You see that I brought it actually. Where did I keep it? I've forgotten. Yes, cooling glass. That sheet, that is a polarizer actually. Cooling glass sheet. It is a polarizer. Yeah, it is here. I will show it. Cooling glass sheet. This is a polarizer. This one is a polarizer. You can do an experiment. I will show you what type of experiment you can do it using a cooling glass, but don't remove it like this. It is a cooling glass sheet. And what the sheet that you have on the surface of a calculator. Suppose you have a calculator. If you have a spoiled calculator, on the display side, you break that calculator, you will get a thin sheet. That is also a polarizer. Quartz crystal is a polarizer. And there are so many materials available to do polarization. Okay, now let us take such a crystal, okay, such a sheet. I'll take a small sheet, practically produced sheet where all the molecules will have a particular direction. Suppose the molecules are arranged like this, and the axis of the crystal is like this, pass axis, which allows the vibrations to pass through. This is the axis, and all the molecules will have their axis like this. And all these vibrations parallel to the axis of the molecules are absorbed. Okay, this is called pass axis, right? Molecular axis is like this. Okay, now pass an unpolarized light to this one. What is unpolarized light? A light which contains vibrations in all directions like this, right? It contains vibrations like this, vibrations like this, all types of vibrations. When they move and hit the surface, only these vibrations are allowed to move out. Am I right? Electric field vibrations coming out are only these vibrations. Like this, like this. These vibrations come out. What about other vibrations? Absorbed. Completely absorbed. Now this is called plane of vibration. This is called plane of vibration. The plane which contains vibrations is called plane of vibration. and the plane which does not contain vibration. Here these vibrations are strictly cut off, isn't it? So the plane which doesn't contain vibration is called plane of polarization. Plane of polarization is the plane in which there are no vibrations at all. Plane of vibration is the plane in which there are vibrations. What is the angle between them? Definitely angle between them is 90 degrees. So plane of vibration and plane of polarization are aligned at 90 degrees. They are always at 90 degrees. Okay. Now, okay, let the light pass in and let it, I will remove this, okay. And the vibrations are like this and they pass like this. Now, whether this light is polarized or not, just by keeping your eyes here, can you say that this light is polarized? We can't say. Then how to check it, sir? Take another material like this. That is called analyzer now. The working is same, just the name is different. This is polarizer, and now we will have an analyzer. What we will do with the analyzer? Keep that analyzer here like this. Keep that analyzer here. How to keep it? Yes, keep it like this. So when the analyzer is kept like this, its axis is like this, right? Now what happens? The vibrations allowed by this first polarizer are like this. Vibrations are like this. Whether they can pass through this, of course, initially when the light was incident, it was containing all the vibrations. It was in all the axes and all the planes, and that was called unpolarized light. And this, the axis of this crystal was like this. I'm not mentioning about the axis of the molecules. Pass axis is like this, which allows the vibrations, and these vibrations are allowed to pass through, and they came out like this. In the sense, they are the electric field lines, electric field directions, and electric field has passed through and it has come out. Now, the axis of this crystal and the electric field vibrations are parallel. Now they can pass through this crystal also. You will get maximum light now. So if you observe it now here, you can see maximum light. Am I right? Now turn it. Turn this crystal or that sheet, analyzer. So this is polarizer and this is analyzer. Turn the analyzer slowly till it becomes 90 degree. What happens? When you turn this analyzer so that its angle is at so if you turn it like 90 degree, what happens? Now the axis of this is like this, and these vibrations go and hit it like this. This polarized light contains vibrations only in a single plane now, and those vibrations are perpendicular to the axis of the other, pass axis of the other crystal. They will never pass through. And what about the light here? Light intensity becomes 0. This is how you can test it. So whether the light is polarized or not, you have to test it using an analyzer. Now again turn it by 90 degrees. Turn it like this. Okay? Now again you get maximum light, right? You will get light here. Again this becomes maximum. Hope you have followed. So if you have a polarizer and analyzer in front of you, you can test whether the light is polarized or not. So unpolarized light is made to fall on the polarizer. If this is the pass axis, only these electric field vibrations will be passing out. Hold the analyzer parallel to it. Then the electric field vibrations parallel to this axis will pass through the analyzer also. After passing through the analyzer, they will reach you. You will get maximum light. Am I right? Now, if I turn it like this, little by little, and the intensity goes on decreasing now. When I turn the axis, now the axes are not parallel. The axis may be at 30 degree, 45 degree, 60 degree. When the axis becomes 90 degree, the intensity out of this analyzer completely becomes 0. Why? You don't receive any light coming out of these two, because the vibrations allowed by the first polarizer, and they will be blocked by the analyzer because the axis of the two will be at 90 degrees. The vibrations allowed by this will not be parallel to the axis of this, but perpendicular to the axis, so no light comes out. Turn it once again, you will get maximum light. So when you turn the analyzer by one full rotation, you will get maximum and minimum light twice. Now this is polarized light. Now suppose I will give you some amount. Sir, some light is coming from a window, through a window. Whether it is polarized or not. How can I test, sir? Already we are receiving light. We want to test it whether it is polarized or not. Very simple. Take an analyzer, sheet like this, or a cooling glass. Hold it in front of the light. I want to test that light whether it is polarized or not. I turn it like this. When I turn it like this, sir, I get light now. What about here? Sir, I get the same amount of light. Like this, same amount of light, same amount of light. Whenever I turn the analyzer, if I get the same amount of light, then the incoming light is unpolarized. Why? Because when I hold the analyzer like this light was coming out of this and it was reaching your eyes. When I hold the analyzer like this light is coming and reaching your eyes. When I hold it like this light is coming. That means the incoming light was having vibrations in all the axes. It was having vibrations like this and they passed out. When I was holding like this, it contained vibrations like this, they passed out. When I held it like this, these vibrations passed out. That means incoming light contains all the vibrations. It is an unpolarized light. So when you rotate the analyzer, if there is no intensity, if there is no variation in the intensity of light, then the incoming light is unpolarized light. Instead, something light is coming in and I turn it, maximum light I am getting. When I turn it like this, the amount of light goes on decreasing. When I hold it perpendicular, the amount of light becomes 0. Again, when the amount of light is increasing, it becomes maximum. As I do here, when I hold it like this, I get maximum light. When I hold it like this, I get minimum light. Again maximum light, minimum light. Whenever the axis of the analyzer is parallel to the vibrations, I get maximum light. And whenever I hold the analyzer perpendicular to the incident light, I get 0 light, maximum light, 0 light. And if it happens twice, maximum twice minimum in one full 360-degree rotation, incoming light is unpolarized. Hope you have followed this, right? So for that one you need already polarized light. Sir, who is polarizing it then? Somebody might have polarized, some processor might have polarized it, whatever it is. We can check whether the light is polarized or not. Whereas, if you turn this, if you treat this as an analyzer and turn it, you will find that when it is like this, you receive this light, right? Vibrations like this. When you are like this, these vibrations will pass through. It is an unpolarized light. So I don't know whether I can show it properly here or not using this two Polaroid sheets. These are the Polaroid sheets, artificially produced Polaroid sheets. I don't know whether I can show it clearly or not. So when I turn it, it becomes dark and bright at a particular place. And now the amount of light, actually I have to incident light from back and I have to show it to you, but it is not possible here. So when I turn it, I will show it later in PPT. I can make it a separate video and I can show it. See, when I turn one one over the other, once the light becomes dark, and when I turn it further, the light becomes bright. Bright and dark and bright and dark. I don't know whether you can see it or not because I don't have another person's help today. I am doing the video by myself. So it should become maximum, minimum, maximum, minimum. I can do it in a separate video and I can show it, not now. Okay, you can do that, and you can take two calculators, spoiled calculators, and break them, take the sheet from the display, and you can do that. Or you can do a better example, better experiment. What you can do is, that also I will show it in the PPT. What you can do is, take that cooling glass polarizer, type something in the calculator. Light coming from a calculator is polarized, because it is produced from digital LCD display. That light is polarized. It contains strictly vibrations in a single plane. But you can see that, no problem. If you contain some or other electric field vibrations, you can see that. You need not have all the electric fields. Now, hold that cooling glass in front of the that calculator, go on turning it. At one angle, you will miss whatever is written on the calculator. Suppose you write some 888 and rotate it. At one position you can read 888 through the cooling glass. At another position you can't read it. Because when the axis of that polarized analyzer, cooling glass sheet, Polaroid sheet, and the vibrations coming from the vibrations of the light emitted from the calculator are parallel, you can see the letters. And when you hold it like this, the vibrations of the light coming from the calculator are perpendicular to the analyzer. You can't see that. You can do this experiment very easily, and even the light coming from mobiles, some digital displays, they are all polarized. Okay, that is one thing. Okay, moving on. You know, you have studied what are polarized lights, what is unpolarized light, and what is polarization. Which property of light shows that it is transverse in nature? Polarization. And if light is transverse, it can show polarization. If light was not transverse in nature, it would not have shown polarization. Can sound waves be polarized? No, because sound waves are longitudinal. There is no question of polarization at all. And how to represent a polarized light in the paper sheet? Drawing vibrations like this. Unpolarized light, how to show it? What is plane of polarization? What is the plane of vibration? How they are aligned? All these simple questions. Okay, and describe an experiment to show how that, or describe an experiment to test the polarized light. So take an analyzer, turn it, and if there is no variation in the intensity at all, that is what happens here. If there is no variation in the intensity, because if you turn it like this, either one or other vibration will pass through. If there is no variation in the intensity, then the incoming light is unpolarized. But what happens here is different, right? If there is variation in the intensity from maximum to zero, then it is polarized. So describe an experiment to explain polarization or test whether the light is polarized or not. That is another question. And if you can, and one thing I can explain here. One important point to be discussed. Sir, you say that I will raise a doubt and I will clear it myself, okay? And you just think of yourself and later on I will answer. I don't answer it now, okay? For the time being I don't answer it. You have to answer it, but answer should come from your side. Sir, you say that suppose this is a polarized light. What are these arrow marks? They represent electric field vibrations, correct? This is the propagation of light. These represent electric field vibrations. Now suppose if I hold an analyzer like this. I will hold an analyzer. Analyzer sheet is held like this. Just to show that it is an analyzer and its shape, I am doing like this. This is the path axis, not the axis of the molecules. When it is held like this, what amount of light that you get here? It is the full amount of light, correct? There is no doubt, because amount of light that you get on the other side is maximum, intensity is maximum intensity. Sir, you said that the intensity becomes zero when you hold this analyzer perpendicular to this axis, right? You said that you will get zero light when I hold perpendicular to the axis like this. Then intensity becomes zero, not maximum. Why you need to hold it perpendicular? Why can't you just tilt it, right? Suppose the analyzer is held parallel to the vibrations like this, you get maximum light, right? Light is maximum. Just if I tilt it like this, from this position to this position, okay? A small tilting, won't it enough? Like this. Because these vibrations will hit it like this, right? These electric field vibrations now, they are not exactly parallel to the path axis of the crystal. Am I right? Now, won't it enough if you just tilt it a little bit away like this, make the intensity zero? Now it is not zero, it will be less. Did you follow this? As I turn the analyzer little by little, the intensity goes on decreasing and decreasing and decreasing. It becomes perfectly dark, perfectly zero intensity, only when this analyzer is perpendicular to the vibrations. Why you need to keep it perpendicular? You see, these vibrations can now pass through. When I just tilt it a little bit, won't the vibrations be blocked? Because the axis is not parallel to these electric field vibrations. Why don't they get blocked completely? Why some amount of light can pass through? That is my question. You should answer. I don't know how to really answer. I will answer it in the next class. Okay? So that is the thing about the introduction to polarization. So read this introduction. You will have some tiny questions, 1 mark, 2 marks question. Then we will move on to 2 important derivations in this. So till then, keep studying. Thanks for watching my class. We will meet in the next class. Thank you.